Hello and welcome back to part 2. Hello and welcome back to Calculus 3. This is the part 2 of our tangent planes, linear approximations, and differentials, and whatever else is in this lecture. It's a lot of stuff. So last time we talked about tangent plane, and we started by defining the tangent plane where we used the standard formula for the plane where we replace the normal vector n with the partial derivatives in respect to x, y, and z. And I showed how this is changed, and then we worked out on 2 examples. We also redefined that tangent plane in case that you have f of xy, and that was the formula that we used. So now we are going to take this exact formula here and define linearization. But before I jump into linearization in Calculus 3, I have to travel back in time and talk about what the linearization is at all, and then why we used to need it, because today we have computers, we don't need any of this stuff, but you know, we can always honor our ancestors by learning all of this. First, going back to Calc 1, as I usually do. So in Calculus 1, the question is, what is the square root of 10, right? That's the question in Calculus 1, and believe it or not, you can calculate this very closely, right, if you use linearization method. So what was the idea? The idea is that if you have any kind of a function and you draw a tangent line at the point A, and then you want to compute, but you want to compute some other value, like in our case we want to compute a 10 for the function f of x equals square root of x. You see that if you do the tangent line at the point that it's easy and nice to compute, like 9 for instance, you will get the tangent line whose y values are very close to original y values in some neighborhood around that point. So you are not allowed to stray too far from the point where you want to compute. So you find the closest nice value that you can compute by hand, and you come up with the tangent line at that point. And then if you zoom in, right, at location here where 10 is, you see that the location of the function, the true value, which is the black line, and the approximated value, which is the red line, are pretty much the same value. So it's a very good approximation, and it's very easy calculation. Now obviously all of this today is obsolete because we have calculators, computers, and all of these things to compute these values, and we don't really have to worry about linearization at all anymore, unless you're doing some really advanced stuff way up there in the coursework. So what am I going to do? I'm going to find the tangent line at the value a equals to 9. So that's my, well, I mean x equals a, which is x equals 9. And then I'm going to compute 10. So the idea for that is we can write the tangent line in one line. Instead of doing the whole procedure for tangent line, we can just use the combined formula. Now this is the tangent line formula, but we call it linearization because you get the linear, like tangent line is a linear line. So this is the formula which we used in Calculus 1 to calculate the tangent line in one shot. So if you calculate your derivative f prime as 1 over 2 root x, then it's very quick to compute linearization for this problem. We have 1 over 2 root 9, because you are supposed to plug in, sorry, the first one is just square root of 9, plus the derivative goes here, 2 square root of 9, and then x minus 9. So a is equal to 9, you have the function computed at 9, the derivative computed at 9, and then a equals 9 for the last parenthesis. If you work all of this arithmetic now, you get 3 plus 1 over 6 times x minus 9, and then L of x is equal to 3 plus 1 over 6 x minus 3 halves when you cancel. Now 3 halves is 1.5, so L of x is equal to 1 over 6x plus 3 halves, right? So this is the tangent line, this is the red line, and now we claim that function computed at 10 is approximately equal to the linear line, right? When you plug in 10 into linear line, so you get 1 over 6 times 10 plus 3 halves, and you have, that's 5 halves, 8 halves, it's 4. How's this 4? No, it's not 4 because I can't compute. This is 5/3, not 5 halves. 5/3 plus 3 halves. The common over here is 6. So 10 and 9, 19 over 6. Okay, 19 over 6. So we computed that f of 10 is approximately 19 over 6. Now we can use our calculator to just see how well this approximation went in this calculation. So 19 divided by 6 is equal to, so this is approximately 3.1666 forever. And if we take a square root of 10, square root of 10 is approximately by the calculator given as 3.1623. Well, yeah, look at that. It's half of cent off, half of 1 cent off. This is pretty good, right? For the calculation that we can do by hand, you know, stick in a sand kind of deal. Yes?
So basically, whenever we have this kind of situation, we would the x would be given to us as well.
Well, the number 9 is not given to you. I am only, you are only given in these situations what they're looking for. It is your job to know that if you're looking for ln3, the best value to use is e, because it's about 2.7. If you're looking for square root of 15, use 16. If you're looking for square root of 120, use 121, that's 11. Right? This is all Calculus 1 review. Now we're supposed to bump this into Calc 3. So the idea here is to realize that as you are looking for the tangent line, there is a neighborhood right around that tangent line where the values of the tangent line and the values of the function are very close, as you've seen in our answers, right? In the good old times, just go 50 years ago. That's how far you have to go. No computers, no calculators, no cell phones. 50 years ago, calculation like this is a very valid calculation, because how else are you going to get the square root of 10 or square root of 17 or, you know, square root of 17.9? Like, what do you do? So engineers used to travel with the slide rule, or they used to travel with a book called log tables, and that book contained the values of logs and square roots and cube roots and trig values, so that as you're working on your engineering projects and, you know, square root of 7.3 comes up, you actually look in the book and you flip through the pages and you find square root of 7.3 is equal to, and it gives you the decimals. All of those values were obtained this way, right? So it's not a chicken or egg kind of deal. Definitely calculators, you know, were invented. And the interesting thing, right, to invent all of that stuff and to do all of that engineering to come up with calculators and things, these approximations were done. Apparently for a Manhattan project, right, where they were designing the nuclear bomb, they had a legion of graduate students working on calculations because, you know, all of these values had to be computed to whatever amount of decimal places. There were no calculators or computers. So you had hundreds of graduate students working linearization problems to come up with values that were supposed to be very precise and very, right? All of this today is obsolete, including the Calc3 stuff that we're going to do now. Now, how does the Calc3 stuff work? It works the same way. You don't have now the function with the tangent line. Now you have some kind of surface, and you have a tangent plane. Tangent plane is going to touch, or as we say, kiss the surface at a single point, making, again, a ring around that point where the values of the surface of the object and the tangent plane, they're close together. The further away you go, the further away those values are. So that's why you always have to look for a close by values. Please observe that if I'm trying to use this x value here, the value of the function and the value of the tangent line are really far apart. So it's useless, which is why you want to set the tangent line close by when you, right? So it's your job to figure out what are the appropriate values to use. So now, what is the formula for linearization in Calc3? So Calc3 now. Well, it's the same function we had earlier. We called it z equals, and then the function, now we're just going to call it L of xy equals. So it's absolutely the same formula. So linearization and we are going to say L of xy is going to be our fx computed at AB times x minus a plus fy computed at AB times y minus b, and then plus f of AB. I hope you see that this is a natural extension of your 2D case, because if I am to scratch off the y term completely, and you just kick out all b's, you see how that's actually one-dimensional version of it, I mean 2D version of it. So if you are to just get rid of the y term, fy, if you get rid of that term and you just scratch all of the b's out, it becomes your linearization in Calc1 formula. Now, for those of you that want to extend your knowledge in Calculus 3, can you come up with a linearization version in 80-dimensional space? You should be able to write it out like this, right? Because you see the pattern, right? You will need 7 of these partial derivatives, and each one of these points would have 8 values inside, and it's 8-dimensional problem. It's fine. You can put this for any dimension you want. So this is the linearization, and all we need to do now is an example. Now, there are examples done in a book, so please look at those. I'm going to take a look at linearization from homework. So let's take a look at something. I'm going to go with the cheap one because the problem is symmetric. Now, would you like a square root problem or ln problem? Square root problem, fine, that will be 28. So the function fxy is given as the square root of x squared plus y squared, and they want to estimate of the value 3.1 and negative 3.92. So this is all it's given. You're supposed to do the linearization so you can compute this function. Now, why is the whole thing obsolete? Because you have x and a y. Just plug them in, use your calculator. You are done in a minute, right? That's it. There is no reason to do any linearization today because we have computers, we have calculators, and you can compute the exact value. Well, the exact value to a number of decimals that are given in the calculator. You can compute that value, and it's going to be far better than when you do linearization. So there is absolutely no need for any of this anymore. Well, let's honor the ancestors, right? Let's see what happens and how it was calculated before calculators came about. So what do? We first figure out what is the point at which we are going to linearize. What is the easy point to linearize? Well, clearly, 3, negative 4. Thank you. So 3, negative 4. You get that by looking at the other point, right? 3.1, well, call that 3, and negative 392, call that negative 4. These are the good values that we can use. Now, find our fx. So now this is going to be 2x over the square root of x squared plus y squared. And then there's a 2 in front as well, so 2's will cancel, which leaves us immediately, because it's symmetric, remember I picked the cheap problem because I'm lazy, is y over square root of x squared plus y squared. So we have the partial derivatives, which we need for our formula up there, and we immediately compute the linearization, the tangent plane, so L xy is going to be equal to, and now fx computed at AB, so that's computed at, right, this is your AB. So what do I have? I have x is 3, so I have 3 divided by square root of 3 squared plus negative 4 squared. That's beautiful, that's 5. Times x minus 3. Plus negative 4 over square root of 3 squared plus negative 4 squared times y plus 4, and then plus the square root of 3 squared plus negative 4 squared. That's the function computed at AB. All I did is I plugged everything in, and now we work out our algebra. So this is 3/5 x minus 3 minus 4/5 y plus 4 plus 5. 3 squared is 9, 9 plus 16 is 25, square root of 25 is 5, so we have those 5s there. You could simplify this more if you distribute all of these. So L of xy is 3/5 x minus 4/5 y, then we have minus 9/5, then minus 16/5 plus 5. L of xy is 3/5 x minus 4/5 y. And now this is negative 25 over 5. That's 5. Negative 5 plus 5 is 0, so they'll cancel. And your linearization is this. Woohoo! So now, function computed at... Oh, I used the... okay, fine. At 3.1... It's not supposed to be 3.1, it's supposed to be 3.06. I can change that. We did not use this at all. 3.06. I picked the wrong, I picked 3.1 from problem above by accident. So just change 306 so it's exactly the problem in the book. So 306, there we go. And negative 3.92 is approximated by computing the L at 3.06 and negative 392, which is equal to, now 3/5, that's 0.6 times 3.06 minus 0.8 times negative 3.92. And now, in obviously all of our laziness and entitlement, we go 0.6 times 3.06 is 1.836 plus 0.8 times 3.92, 3.136. So for the total of, that's a 12, that's a 7, that's a 9, that's a 4. 4.972. 4.972. And that's linearization. So what you do for linearization is the same thing, like in Calculus 1. You find your tangent plane, which we achieved here, and then compute the point you want to compute in the tangent plane rather than. Now again, why is all of this useless? It's useless because you could have plugged in 3.06 into original function and just use your calculator to compute the values and be done, right, with the better precision and everything. So we have a square root of 3.06 squared plus 3.92 square will kill the negative, so I don't care about typing the negative. So if we are, this is not exact, but f computed at 3.06, this is a check. So f computed at 3.06, comma negative 392 is given as 4.9723, actually, 3. Guys, this is 1/10 of a cent off our calculation that is done by hand versus the calculation done on the computer. But again, right, it's cool to know things. At least when someone tells you, what do you know? I can compute the square root of 3 by hand. Well, what do you know? Right? At that point, you win the argument immediately. So yeah, it's cool to know linearization. The last part of the lecture is called the differential, which is another one of these. Now, the differential does not approximate values. Differentials approximate change in values. So they're a little bit more valuable than linearization in terms of current times, but still you can calculate the change very quickly, the exact change. So what is the idea? The idea is that, let's say in the summer, your tire pressure should be lower than in the winter, because in the summer the temperature, outside temperature, is higher. So if you consider ideal gas law, should have better models, but that's okay. PV equals nRT. This is constant over here. You have the pressure and the volume of the tire and the temperature. Observe what happens. Volume of the tire is the size of the tire. You can't really make the tire bigger. It is rubber, it's elastic to some point, but past that point it's just going to explode, as you can see all the debris as you're driving on major highways. So as you can see over here, if the volume is kept constant because you can't inflate tire anymore, with the rise of the temperature, which is the friction between the tire and the road, that keeps you on the road. That's a good friction because you want a lot of grip. Otherwise, you'd just be sliding all over like on ice. So you want the friction between tire and the road, and when there is friction, there is heat, right? So there will always be heat between the on the tire due to the contact with the road from friction. However, the temperature outside could be, like at Cornell, -30, or it could be like here in New Jersey, 130 in the shade. So, right, there's a lot of differential in temperature there. So with the higher temperature, higher the pressure, that means, yeah, where does it go, right? You can't go anywhere else. The tire does explode. So it is important to make sure that in the winter, right, the pressure is kept up high for your tires, but in the summer you should go lower because the temperature from the road plus the temperature of the surrounding can bring up the tire. So now what are we talking about here? Well, we can talk about the change in pressure, we can talk about change in volume, we can talk about change in temperature, right? And the good things about those is they all can be computed, right? So we do want to know the change. You can also calculate the change in your body mass index, the change in your body mass. You can calculate the change in mass of the car plus you. As you're driving, you are using up the fuel. So the mass of the entire system is getting lighter as you are driving. Some of these changes are sudden. They cannot be noticed easily. And some of the changes are visible, right? So differentials calculate the change. Again, this was very useful in the past because you didn't have to calculate the exact numbers. Let's take a look at the idea. So say you have a ball, just a regular basketball or whatever, whose volume is 4 pi over 3 r cubed, right? That's the volume of the ball. And then you notice, because this is something that you can easily measure, you notice that the radius, which used to be 3, grew to 3.15. Whatever units, inches, centimeters, meters, I don't care. The question is, what is the change in volume? Yeah, we have a calculator. Plug it in and calculate the exact change, right? You don't have to bother with anything else. If you have 3.15, you plug that in, you calculate the volume, then you calculate the volume at 3, you subtract the two numbers, and that's the exact change in volume. But, as we stated, in good old times, there was no calculator or computer to compute that quickly, so we come up with the clever ways around that calculation, and that would be differentials. So differentials in Calc 1 again. So Calc 1. Differential was very easy to understand because you start with y equals f of x, which is your pre-calculus formula. And you take derivatives. On one side you use Leibniz notation, on the other side you use Newton's improved notation with the prime instead of the dot. And now you just move dx to the other side. This formula was the differential formula in Calc 1, where we say that the exact change in y was approximated by dy, where delta x is exactly dx. So those are the same. So your domain values are the same, and the output value is approximated by the formula. So you were able to approximate the change with this. Again, not the value, the change in value. So now what do we do for Calc 3? We just bring in another dimension in here, right? That's all we do. So for Calc 3, what do I have? I have z is equal to f of xy. I have some kind of a surface there. And now I want to calculate delta z. See, delta z is equal to z2 minus z1. That's exact. But again, we want to honor our ancestors, so we'll say delta z is approximated by dz. And dz is given by partial derivative at ab times delta x plus partial derivative fy at ab times delta y. And this is the formula for differential in Calc 3. So the derivative times the change, partial derivative in x times the change in x plus partial derivative in y times partial y. Times change in y. So now we can calculate the thing. So let's see another homework example to work this out, and that's it. How about problem 34? It's a log problem. Z is equal to ln of 1 plus x plus y. And the x will change from 0, 0 to negative 0.1 and 0.03. This is 1 plus. I think I have to change the tip on this pen because it's starting giving me problems here. All right. So what do we have? Well, first off, I want to calculate delta x and delta y. Those are the change in x value and change in y value. And the formula for that is always new minus old. That's the best way to remember it, right? It's the new state minus old state. Sometimes these changes are positive, sometimes are negative. So delta x as new minus old. New is negative 0.1 minus 0, so negative 0.1. And delta y, new minus old, 0.03 minus 0 is 0.03. I need my partial derivatives, so fx is going to be 1 over 1 plus x plus y, and fy symmetric, 1 over 1 plus x plus y. Remember that derivatives of ln functions are always function as is copied in denominator plus its derivative on top, and then you put the derivative on top. So the argument as is goes in denominator, and then its derivative in respect to x here. But derivative in respect to x is 0, 1, and 0. So it's just 1. Now, we say that change in z is approximated by dz, and dz is derivative computed at ab. So that's 1 over 1 plus And that will be 0, 0. So plus 0 times the change in dx, which is negative 0.1, plus 1 over 1 plus 0 plus 0. So this would be another partial derivative, computed at a, b original values, times the change of 0.03. So all of this is just 1 times this, so negative 0.1 plus 0.03 for a total of negative 0.07. So our calculated change is approximately equal to negative 0.07. Did we have to do any log calculations? No, right? All of this you can do with a stick and a sand, right? And no reason for calculator at all for a calculation like this. Now, obviously, since we live in a time when we live, you will just say, all right, let me compute this in a calculator and see what it is. So we have ln of 1 minus 0.1 plus 0.03, and the value, and then when you subtract 0, 0, but that's ln 1, which is 0, so we don't have. So calculator gives that delta z is equal to negative 0.0725706928. This is what the calculator gives us. And if you take a look, I mean, come on. As long as the 2 decimals work by percents, we're good to go. I mean, not everyone is interested in particle physics. So, yes.
So when we went from 1 plus x plus y, then you just plug in the first point, right?
Well, I plug in the second point to compute the because it's always the second minus first, right? It's new minus old.
I mean, like, so the
Wait, are you talking about the last line or above?
when we went from the denominator being of fx and fy.
Oh, here.
Yes, and then the denominator went to 1 plus 0 plus 0.
Yes, these are your A, B. This is the first point. Yes. So you calculated the change off of the first point. Ta-da! Right? Cool. All you need to do is do some homework exercises. You'll be fine. I hope that's all. Yes?
Is 12.7 up here on my line?
Should be. 12.7 chain rule, yeah.
This was
Goodbye.
this